Welcome back, everyone. We're in the wastewater stream, day 2, EOCP 2021. It's the home stretch, saving the best for last. We're going to talk about keep your lagoons and meet your targets. We have Chris Haworth from Veolia presenting shortly, and I just want to tell you a little bit about Chris. Chris Haworth is a registered professional engineer in BC with 25 years experience in water and wastewater treatment. He has worked for both private and public sector organizations in Europe and Canada. He is currently responsible for Veolia's municipal business development in Western Canada. So we're looking forward to this, Chris, and I'd like to welcome you to the stage.
Thank you very much. So, turn this on. Okay, so thank you very much for the introduction, and I can take this off now. You can see my face. So I appreciate I am the last thing of the day, so thank you very much for attending this presentation. I'll certainly try and keep it on time. And yeah, it's all about lagoons and how you can keep your lagoons and still meet your treatment goals. So I'm guessing the slides are just loading up at the moment. Okay, so yeah, give you a sense. I don't see anything on the screen here. Is that okay? It's there we go. Perfect. So to give you a sense of what I'm going to be talking about, I'll start off with a little bit of the context, then get into some of the challenges that the lagoon systems face meeting targets, and then how those challenges have been solved, some examples of that, and then we'll finish up with a little bit on specifically on the operation and maintenance side of that. Not seeing the slides exam. Okay, good. So lagoons are great. I mean, if you're a small or medium-sized community, you've got the land, they are probably the best way to go. I'd certainly probably have one if I could. They are very simple to operate and maintain. From an operating perspective, wastewater comes in one end, goes out the other end treated. There's really not much to do. If you have mechanical aerators, then you need to maintain the blowers, maybe some instruments, some valves, but really there's not a lot to them. Very simple to operate and maintain. They also look after the sludge. Every few years, maybe a few decades in some cases, you get the sludge out, dig them out or whatever, dredge them, and that's it. Very simple. Unfortunately, nothing's perfect. And they do have limitations. They are very large, so sometimes the town will grow up around the lagoon site, so you can't just build more lagoons if you need more capacity. But perhaps specifically for this presentation, I'm going to be talking mostly about their performance limitations, and by that I mean effluent quality, achieving the effluent targets that people are looking for these days and into the future. So specifically, something that's happened in the industry which is causing challenges for a few people is the wastewater system effluent regulations. It's Environment Canada, it's federal regulation, applies across Canada. It was introduced in 2012, and increasing numbers of people are having to comply with the WSER regulations. They are being enforced as well, so it's certainly on more and more people's radar. There's a couple of parts of the WSER regs that I'm going to be focusing on with today's presentation, and they're both to do with ammonia. So you can see on the top there, unionized ammonia. The WSER has a specific limit of 1.25 milligrams a litre of unionized ammonia. It's a sort of hard and fast. You must be lower than that. They also require non-toxic effluent. Those two things are related because unionized ammonia is toxic to aquatic organisms. So, and actually the 1.25 is a little bit sort of a red herring. It's not a very useful number for a couple of reasons. One is because you can kill fish, which is how this toxicity is measured, a lethality test. You can kill fish at a lower concentration than 1.25 milligrams a litre. I've seen data showing fish kill down to sort of half a milligram a litre of unionized ammonia even. So the 1.25 is not good to rely on. Another reason it's a bit of a red herring is because the amount of unionized ammonia you have in your water depends on various things, but maybe just to back up a level, in water, ammonia can be unionized or it can be ionized. Ionized ammonia is NH4+, unionized ammonia is NH3. I see a lot of confusion around this because you often see people talking about one or other of those or writing down NH3 or NH4 when they really mean total ammonia. And total ammonia is both of those things. It's the sum of both of them. How each of those exists in water, or the fractionation between them, how much is ionized compared to how much is unionized, depends on a few things, but mostly pH, and temperature is also very significant. The more alkaline your water, the more of the total ammonia will be unionized, will be NH3, and then the more toxic your effluent will be, or your wastewater will be. So like I say, that 1.25 is a bit of a red herring. It's a moving target because pH varies in lagoons. Different seasons, if you have an algae bloom, whatever it might be. pH is not a sort of fixed thing that stays the same throughout the year or even from day to day. So a much better way to look at ammonia is as total ammonia nitrogen. If you're designing a system to remove ammonia, to meet these WSER limits, to not kill fish, total ammonia nitrogen is the thing to focus on. If you look at the graph here on the screen, you can see a red zone. This graph, I should say, by the way, is results from lethality tests. There's different ways of testing it, but bottom line is you put effluent in a tank full of rainbow trout, leave them there for 96 hours and see how many survive. If you kill more than half of them, then by the way some of these tests are done, that's a fail. So you see that red line down the middle, that's 50%, that's half of them being killed or surviving. And if you're above that line, then you failed the test, and you can see that somewhere sort of beyond higher than 10 milligrams a litre of total ammonia, all of the fish died, or almost all of them. You see there's one which is not quite there, 70% odd. Below 10 milligrams a litre, you're more likely to pass the test. Certainly if you're at 5 milligrams a litre of total ammonia nitrogen, you should be safe. You should pass the test, even if you've got relatively alkaline water. So designing these systems, when we're looking at putting one of these, a solution to this in somewhere, 5 milligrams a litre is a good number to design to. How do you remove ammonia? In wastewater, it's basically going to be a biological system. And specifically, there are a group of organisms called nitrifiers that nitrify ammonia to nitrate. So those are the organisms you need to remove ammonia, to convert it to nitrate. Nitrate is not toxic to aquatic organisms. The problem with that is that nitrifiers are really quite sensitive. They don't like cold water at all, and they grow very slowly. So what you can see here on the chart is the growth rate of nitrifiers at different water temperatures. In the summer, 20-25 degrees water temperature, nitrifiers grow really quite fast. They're reproducing, they're removing ammonia. At the other end, sort of more like winter temperatures, 5 degrees C or even lower, nitrifiers slow right down. So it's not like they die, but they don't do much. They don't remove much ammonia at those lower temperatures. What this translates to in the real world is a lagoon system in the summer probably does a reasonable job of removing ammonia. It might well be below 5 milligrams a litre in its effluent. But then winter comes on, and it basically stops nitrifying. So it's going out of the strength it's coming in at, and that's when the failing of the lethality test is likely to happen. So that's a problem. If you've got that problem, if you have the potential to be killing fish and you need to meet these regulations, then you need to do something. And what does that look like? What would good look like? Well, I'd argue a good place to start is keep what you've got. Don't throw the baby out with the bathwater. I'm using lots of acronyms here, but analogies rather. But add the cherry to the top of the sundae there. Add something to it, but keep what you've got, because what you've got cost a lot of money, and is probably doing a good job for what it had to do for the last few decades. Removing BOD and TSS, lagoons generally do a pretty good job at that. So it's just about adding something to your lagoon system to do that extra thing of removing the ammonia. So what would that thing be? What would be good for that thing to achieve? Well, firstly, it should be simple. You've got a lagoon, you've got folks who know how to operate the lagoon. Ideally, this thing you're going to add is as easy to operate and maintain as the lagoons. So the folks who are currently operating the lagoon can take this new thing on as well. So keep it simple. It'd be good if it was relatively compact. That way it'll fit on the site. Maybe getting land nearby isn't available. It's always good to have small systems because they're normally relatively low on capital cost as well. So cost effective is another important thing, capital as well as operating cost, energy requirements or chemicals or whatever. Robust is good. I mean, lagoons are pretty robust. You can throw pretty much anything at a lagoon and it'll do a reasonable job. So same with whatever you're going to add to it. You want it to be able to handle, peak flows and varying loads and all of that. Adaptability is the last thing I would say, and flexibility with that as well. So what if the regs change another 10 years from now, whatever, these things always get tighter, right? So what if your regs, the limits get lower, or you have to remove something else like total nitrogen, not just ammonia, but total nitrogen. Whatever you build, ideally should be flexible enough to adapt to that in future, and expandable too. So I think it's fair to say the market has pretty much settled on attached growth as being a good solution to this problem, removing ammonia from lagoons. Some people I've heard refer to attached growth organisms as huggers, with the others being swimmers. So things like activated sludge systems have suspended growth, and they could be called swimming organisms, swimmers, they're just floating around in a tank. Attached growth organisms stick to a surface. They form a biofilm, and so huggers is a nice name for them. Huggers are good because they're more robust. You can't wash them out. If the flow goes really high, then those swimmers can get washed out of the system. The huggers are going to hold onto that surface and stay there. So they're more robust. You can also hold a lot of them in a tank. If you've got a large surface area, then a lot of that biofilm is going to grow on it. You're going to have a lot of huggers in your small basin. So, high rate, a compact process. Another good thing about attached growth systems is, just like a lagoon, they're a flow-through process. Wastewater comes in one end, goes out the other end treated. You don't need to worry about retention times on your solids, SRTs, solids retention times. You don't need to worry about recirculating anything, RAS, return activated sludge. You don't worry about F2M ratios. You don't even worry about what microorganisms you're growing. As long as the system has been designed properly, then it looks after itself. In one end, out the other. Very simple to operate. Attached growth wastewater treatment solutions aren't new. If you've heard of rotating biological contactors, RBCs, if you've heard of trickling filters, then you've heard of attached growth processes. This is not a new technology at all. Trickling filters are well over 100 years old now, so plenty of examples of the technology. And as you probably get the idea, RBCs, trickling filters, they come in different shapes and sizes, different configurations, these things. Same in this application for removing ammonia from lagoons. There's various manufacturers offering things for this application, and they generally look a little different here and there. There's some similarities, some differences, but what it is safe to say is they pretty much, to my knowledge, they all use attached growth biofilm type technology. So where should you put this thing? This is maybe where I move more into how Veolia does it, because as I said, there are other manufacturers who do it, who offer things as well, and some of exactly where it goes and exactly what it looks like is a bit different. So this is more now moving into how we do it. So we would recommend you put it after the lagoon. You've already got a lagoon which is removing BOD and TSS, so like I said, keep that. That does the heavy lifting. At that point, the effluent's pretty good. There's not a whole lot in there, but there is likely going to still be a lot of ammonia. So it allows what you add, that biological system, to focus on ammonia. So what we use is a technology called MVBR, Moving Bed Biofilm Reactors. You see the black box has now got a little sort of plastic thing in it. That's the media, also called carriers. That is the thing that gives a surface for the biofilm to grow on. You can see the sort of red stuff in that picture. That's biofilm. So put a bunch of those in a tank and it grows biology, it grows biofilm, and that's where the nitrifiers are that remove the ammonia. It's pretty compact, so we kind of call it a lagoon in a box. It's, I don't know, a bit cliche maybe, but yeah, that's a way of looking at it. Just a more compact way of doing a very similar thing. Flow through, so nice and simple. It fits all types of lagoons. So if you've got a mechanically aerated lagoon or if you've got a facultative lagoon, doesn't matter, works the same. If you've got seasonal discharge or a continuous discharge, works as well. There's different ways of applying it. There's some details in there, but basically any type of lagoon, any design of lagoon, this technology can be applied to. Another good thing about it is it handles TSS, including algae. So if you have an algae bloom, or if you have like a turnover, maybe in the freshet, or wind sort of stirs things up in the pond, and you get a bunch of TSS or a bunch of algae getting out of the pond, it's okay. It's not going to block the system. It's a very vigorously mixed tank. So anything that comes in is going to flow out as well. It's not going to block the system. I mean, if you've got a high TSS, it's not going to remove it, so it's not like you might still have an issue on your final effluent, but it won't damage the system, it won't block the system. So I think for a lot of reasons it's a good fit. It really ticks a lot of those boxes that I was talking about earlier on the cherry on top slide. It's very simple, it's flow through, as I've said, just like a lagoon. The biology takes care of itself. It's very compact, so that makes it pretty cost effective, small tanks. You're looking at a retention time, a hydraulic retention time in the order of 4 to 6 hours for this application. So it's a pretty small basin that you need to do that. Very robust. The biofilm is hard to upset. You can't wash it out. If you have something nasty come down the sewer, something toxic, then it's very unlikely that you're going to kill the thing entirely. It's probably not going to like it, but it should survive. And as I said, it handles the TSS. And it also does that flexibility and adaptability thing. It's a biological system, so if one day down the road you don't want it to remove ammonia anymore, you maybe get a total nitrogen limit in your permit, then you can use this very same box that you've built to remove total nitrogen. There's going to be some reconfiguration of things, but the bottom line is if it's removable using biology, then you can do it using what you've built. So flexible. You can also easily expand it, you just add more of that media, so good for expansion as well. So to get into a little bit of the details around what this technology actually looks like, as I've said a few times, you need this media, these carriers. They're about 25 millimeter diameter, 1 inch for people who work in Imperial, and that's the one with the blue background there. That's what we call our Annex K5 media. It's about 25 millimeters in diameter. It's a bit bigger than the older one. The older one is that one at the bottom right there. That's our K1, but same kind of idea. You see at the title of the slide here, protected surface area. That's important because what you need is the biofilm to be in a nice safe place where it's not going to get scoured off or scraped off or whatever. You need the biofilm to be in a protected area, and that's what those little pockets do in the waffle, if you like, giving it somewhere safe to grow. Another important thing is to have a lot of surface area. The more surface area you have, the more biofilm you can grow, and therefore the more treatment capacity you're going to have. So when we look at this Annex K5 media, 1 cubic meter of that stuff has got a surface area of 800 square meters. To give you a sense of what that is, an NHLI surface is 1,575 square meters. So 2 cubic meters of Annex K5 media has got more surface area than an NHLI surface, a lot of area. Lots of area, lots of biofilm, small volume, high rate treatment process. You need to keep that stuff in the basin. To do that, you use sieves, and they keep the media in but let the water out. They go on the effluent side. The holes in those sieves are about 15 millimeters diameter, and the media is 25 millimeters, so that it holds it in the tank. Pretty simple things. They're designed stainless steel and robust so that they don't need any maintenance. There's some details around it, like you see on the bigger picture there. There's actually some air spargers underneath that one. We don't always need those. It depends on the application. So there's some details in exactly how you design these things. One of the key things is actually around head loss. So if you have a very tight hydraulic gradient, then maybe you add more sieves. Normally we'll design for about 2 inches of head loss, 50 millimeters. It is important when you're putting sieves into a system like this that they could catch trash. If you've got a lot of trash coming into this basin, then that's going to be a problem because it might get stopped on that sieve, and over time it's going to build up. It's going to stay in the basin. You do not want that. That said, if you think back to that slide I showed about where you're putting this, it's right at the end of the lagoon system. So the trash should have been stopped in the lagoon, in the ponds earlier. If that's not the case, then there's probably a design issue with the lagoons. But even then, there's a simple fix, which is just put like a headwork screen in there to catch the trash. But like I say, for this application, you shouldn't need to. You also need an air grid. This is not a fine bubble diffuser with rubber membranes, and the reason for that is because you don't want to have to get in there and maintain it. This basin is going to be full of media. So we use medium bubble, sort of drilled lateral type of diffusers, stainless steel, lasts forever basically, certainly lasts for the length of the time of the system, the life of the system. Something to notice on the photographs there is how robustly engineered this is. There's a lot of anchors holding that air grid down. There's the square tubes at the end of the laterals holding those laterals in place, supporting the laterals. The pipe work, you can't really see it, but that's very heavy gauge stainless steel. It's skookum. That's because you don't want to ever have to get in there and maintain it. If there is a problem, worst case scenario, I know the concrete hasn't been poured properly or something like this, you need to get in there and fix the concrete, then it is possible to get in there and deal with these things. It's not ideal, and a part of the problem is going to be that you've got all this media that's going to settle down and sit on that air grid. So you need it to be robust to be able to handle that. So quality is where I'm going with this. There's places in this technology that you can cheap out. You don't have to put as many anchors in or whatever. But if you ever have a problem, you're going to really regret not putting in those few extra anchors. So going with a manufacturer who offers quality and knows what they're doing is important with MVBR technology. It sort of leads on a little bit to the sales pitch. We invented this technology. Our Annex coldness group invented the MVBR technology back in the 80s. We've put in a lot. First one in 1989, over 1,200 around the world now, and over 30 plants in Canada since 2005. So yeah, we've put in more than anybody else. But there are other manufacturers on the market offering MVBR technology as well. It's not the core process isn't patented anymore. So yeah, it's not like we're the only ones you can get it from. Give you some examples of the systems we've put in Canada, and specifically to do with lagoon installations. Some of ours are mechanical plants or whatever else, but on lagoons, our first one was in Saint-Julie. This was in 2005. Saint-Julie is in Quebec. It's near Montreal. Lagoon plant, as you can see. If you look at the lagoon system on the photograph on the left there, the first pond, so the bottom left pond, is fully aerated. That's the cell 1. And then goes out of there to the one above, which is cell 2. Then it goes into this MVBR process. Lagoon guard, by the way, is what we call this technology when it's applied to lagoons like this. So what you can see in that sort of purpley circle there is the lagoon basins. So it goes through the MVBR, the lagoon guard system, then out to cell 3, and there's a few more cells downstream of there. This plant was actually designed primarily for BOD removal. That's why it's sort of early in the process. If you remember from the earlier slide, I was saying about putting it at the end of the lagoon system. This is not at the end of the lagoon system because it was designed primarily for BOD. But when the city wanted to put this in, they thought that maybe one day down the road they might get an ammonia removal requirement in their system as well. So there was a kind of eye to it as part of the design. There's actually 2 basins there, so the thinking was that second basin could become dedicated to nitrification down the road. This is some data. So like I said, it went back in 2000. It went in 2005, but we went back to have a look at it about 10 years later. Because when WSER regs came out, we realized that people were going to need a solution to meet those regs. And we thought we should go have a look at Saint-Julie because that could be part of the solution. This technology, we figured, could do a good job of nitrification, even in cold water. And so we figured we'd go and have a look at Saint-Julie and how that was getting on 10 years later with regard to ammonia removal. So that's what you see on the chart here. The influent ammonia is in green, averaging around sort of 15 milligrams a litre. The temperature is in yellow, so you can see that's getting down to around 5 degrees in the middle of January there, 5 degrees C. And then in the purple at the bottom, that's the effluent ammonia leaving this Lagoon Guard MVBR system, so around about 1. So what that told us was this technology will do a great job of removing ammonia even in cold water. Something else to notice here is the picture on the top right there. That's somebody's gloved hand. We fished out some of the media from that system, and this is 10 years after it went in, and you can see that it's still almost as good as new. I often get the question, do you have to replace the media? Does it wear out? You can see no is the answer. It's just a slight kind of rounding on the corners, but that one that we put in 1989 still uses the original media, so no, it lasts for the life of the system. So moving on, this one is a plant in just on the other side of the river from Ottawa, Gatineau. Because we realized that there was a market going to grow here because of the WSER regs, people needing to find a solution for this problem to meet these regs. We actually funded a PhD student with the University of Ottawa, and he Bradley Young is his name. He spent 3 years of his life doing his PhD, of which 2 years were spent at this lagoon site in Gatineau, where we put in a pilot scale system for this technology and really looked at it from every angle. So you can see that photograph on the right, that's a scanning electron microscope image. What he was doing there was looking at the thickness of the biofilm and sort of what it looked like. He was doing DNA sequencing and cell viability testing to see how much of them were alive and what sort of bugs he had, and it was a PhD, right? So just looking at every single thing you could possibly think of looking at. And we learned a lot, and from that really we commercialized the technology at that point when he finished. That was sort of 2013, he started his PhD. This is some of the data from that work. So the black line at the top is the influent ammonia. This is to the plant, not to our part of it. We were right at the back end. Here we did put it right at the end of the lagoon system, treating the effluent from the lagoon system to remove ammonia. So that black line, that influent ammonia, is the influent, at the front of the lagoon system, averaging around 20, 25, somewhere around there. The blue line is temperature, so you can see there's a big dip in the middle. That's the winter, and sort of day 300 odd onwards. So it got very cold. The water stayed below 1 degree C for weeks at a time there, fully ice-covered lagoon. The red line is effluent ammonia. So you can see staying pretty low, but there is a blip in there in the green circle. And I'm going to come back to talk about that specific thing later. But the point to note here is that's in fall, that's in autumn, when the temperature is dropping, and what we found there is that's a very challenging time. And like I say, I will come back and talk about that a bit more in just a minute. But broadly speaking, we learned a lot, and from this we moved on into commercializing the technology. So a good example of some of the things we've been doing since then is this pilot. We've run quite a few pilots with the technology. This one was one I was involved in. This was in the 2019-2020 winter. So city of Cold Lake, northern Alberta. You can see the lagoon system on the photograph on the left there. It's got 2 aerated cells. In the bottom left, the little ones, the ones below those aren't used anymore. You can see there's 4 down there. Only 2 of them are used. So 2 aerated cells, then into a big facultative cell. That's the sort of tall, skinny one, and then 2 big storage ponds. So it's a storage system. You can see the pilot trailer on the right. That's actually got 2 MVBR trains in it. And in each of those trains, we have 2 reactors in series. So 2 of those tanks full of the MVBR media, one after the other. Probably worth mentioning that we were targeting an ammonia in the effluent of less than 10 on this pilot, and you'll see the data just coming up, and we did that comfortably. We met that comfortably. So we got there right at the end of November. The trailer turned up on site, and then we got the mechanical commissioning done, sort of startup, and then the process commissioning. And then it took a while for the bugs to acclimatize. It was pretty cold water, so it did take about a month for the bugs to settle in and get up to speed. And so by middle of January, we were achieving the performance, sort of the steady state performance. So that's what you see here. This is when everything was sort of settled down, and then we just left it. We just left it running and sort of saw what performance we could get over a good period of time, about a month and a half, so the second half of January and throughout all of February, to see what sort of average level of performance we could get. So influent ammonia is in the black there, about in the middle of the chart, averaging 22 milligrams a litre over this period of time. Down at the bottom, you can see a blue line. That's the effluent ammonia. That averaged 1.5 milligrams a litre of ammonia over this time. That's a 96% removal we were getting. 93%. It was 90-something percent. I haven't got the numbers in front of me, sorry, but over 90% removal of ammonia during that time. The blue dots are the temperature of the water, and you can see very, very low. I mean, normally below 1 degree C. It was very cold water we were treating there. And then the red line at the top is the removal. So that's on the right-hand axis, and as I say, 90-something percent removal there. So this was far better than we needed to get, and we were very happy with that performance. So at the end of March, we figured we had the time, and the water was still cold. We'd proven that it can do what it went to do. But we figured we'd really challenge it, and this is where I'm coming back to that transition thing. So I said earlier in the presentation that in the summer, lagoons generally do a good job of nitrification. The water's warm, the nitrifiers are happy, so the effluent leaving the lagoon generally has low levels of ammonia in it in most lagoon sites. But then what happens is the water starts getting colder. So the lagoons slow down with their nitrification, and then by the time winters come in, there's basically very little, if any, nitrification happening. So at that point, the ammonia concentration in the lagoon's effluent is going right up. The challenge with that is that it's a kind of double whammy, because just as the water's getting colder and is getting hardest to treat, the lagoon, the effluent ammonia concentration is going up and needs to be removed. So this thing that you're going to bolt on the back end, that cherry on the sundae, is sort of having a double whammy. It's got to deal with the ammonia as it's getting more concentrated just at the worst time because of the coldness of the water. And that's a transition in full, basically, as you see that transition. So that's what we then set out to test with this pilot in Cold Lake. But instead of giving it a transition, what we did is we did it in 0 to 100, like literally just like that. We switched some valves. And because we had 2 reactors in series, what had been happening is that first reactor had been removing most of the ammonia. And the second reactor in the train had seen very little ammonia. It was averaging about 2.6 milligrams a litre of ammonia going into that second reactor. So it had been starved, and that's exactly what you would see in a full-scale system because the lagoon upstream has been removing the ammonia over the summer. So you've been starving this black box on the back end, and then you're expecting it to ramp up. And so, like I say, by switching the flow path, that second reactor then became the first reactor and had the full ammonia load after it had been starved for over a month and a half. So what did it do was really the question that we were trying to solve by doing that switch. And like I say, it was instant. It was basically just by switching valves. So at the coldest water, we weren't ramping down the temperature. It was literally like cold water. And same with ammonia. We weren't gradually ramping up the ammonia. It was seeing the full ammonia strength. It was around 20 milligrams a litre on average at that part of the test. And you can see it. They really handled it very well. The effluent ammonia, the same colours being used here. So doing a great job. Again, over 90% ammonia removal, and you see that at the top there. So it showed the robustness of this technology. It's able to handle that transition situation. So a few full-scale examples now. This city of Camrose is building the first Lagoon Guard MVBR system for nitrification for ammonia removal. It's going to be the first plant in Western Canada. Maple Rinders has just recently been awarded the construction project for that. So it's going to be, well, sort of is in construction now. It'll be operating in 2023. It's a 12 MLD system. Camrose has got very tight effluent limits. They've also got stuff around phosphorus and TSS, so we're putting in disc filters as well as the Lagoon Guard system for Camrose. Another example, this one over in Ontario, Castleman. This was built last winter, 2020 to 2021 winter. It was commissioned in early this year. You can see the construction in the photograph on the right there. That's the media being loaded, the big super sacks, so 1 cubic meter sacks of media being put into the basins. Photograph on the left gives you a bit of an idea of what's going on there. It's a storage system, so those 2 ponds at the top there are storage ponds. It's a bit weird, Castleman, because their permits allows them to discharge in the winter and they store in the summer. So that's a bit unusual. Normally the plants I see go the other way around. They discharge in the summer and store in the winter, but it doesn't matter. Like I said, it's a very flexible process, so it can be applied there as well. And if you look on the bottom left, that red circle there, that's the area to focus on. That's where we put in this new system. And that's what you see here. So added a building. This one's also got disc filters for the same reasons. They're in the building along with the blowers and some electrical equipment, and then you've got the basins themselves that you see there on the photograph. So this is actually during the discharge season. In the winter, like I say, is when they discharge. The good news is that they drained all of their ponds down, so they had to stop discharging in May, and by the time May came, the ponds were fully drained, and they met permit, so successful project. Give you a bit of a sense, of the system. If you look at the basins there, a photograph on the left, you can see there's sort of small reactors on the right-hand side of the basin. So there's actually 2 trains in parallel again, so 2 trains of 2 reactors. But in this case, they're not both dedicated to nitrification like the Cold Lake pilot. That first reactor in each of those trains is actually for BOD. So because the effluent from Castleman's lagoons at some times saw relatively high BOD concentrations, we put in a small reactor to first remove the BOD so that the main reactor can just focus on nitrification. So that's why it looks like that. This is a bit of a tangent, and I'm coming up to time here, so I won't talk for long at all about this. But we offer a range of support services, operating support services. So after the plant's installed, both combining sort of digital and human, if I can put it that way. So a bunch of sort of tools, cloud-enabled things, and remote access, and all good things for monitoring and for reporting and diagnosing and all of that kind of stuff. But we recognize absolutely that humans have to be a part of this as well. So remote, on-call people, on-site people, it's putting those two things together, and it's a very flexible thing. If you don't want it, you don't have to have it. If you do, then there's a whole range of things you can choose from around how we can support, the ongoing operation and maintenance of the system. One little example of that, this is a membrane system we put in, and there was an air-locked pump, but the operator didn't realize there was an airlock going on, so he can hear the pump turning, but there's no flow on the meter. So we, using a guy on the end of a phone, and the guy on site has got his sort of video thing, we can tag the valve that he needs to get to, purge the air out of the system, then the pump is no longer airlocked and the system starts cleaning. So it's one example of how you can, one of the tools we offer as part of this whole thing. So just wrapping up now, the Lagoon Guard process is really very simple. I hope I've explained some of that and it sort of makes sense through all of this. So it's very resistant to toxic shocks, handles very wide-ranging flows, adapts by itself, very easy for the operators to look after, very little maintenance. You're looking after blowers and instruments and some valves, so very simple. It can really be used to meet any limit that you need to meet using biology, give or take. If you need to remove phosphorus or TSS, then putting a disc filter on the back end is probably a good idea. That is also very simple as well. So as you saw, Castleman and Camrose both have the disc filters. It can help with meeting treatment capacity needs, and you can even get as far as reuse. If you're putting a disc filter on your effluent, then you're going to be cleaning it up to reusable standards. With that, I'll thank you for the time and see if there's any questions that have come in, or how we do this from here.
I'll put it on. There we go. Thank you, Chris. That was excellent, and lots of nice comments in the chat. There's a few questions.
Yeah.
This one's from Tim. How is the sludge buildup cleaned, and how often does the media need to be cleaned?
Excellent questions. So nitrifiers are very slow-growing organisms. So you do grow a little bit of sludge, if I can put it that way. There is a little bit of biomass that's created in the system, but it is a very small amount. Rule of thumb would be for every 10 milligrams of ammonia you remove, you produce about 1 milligram a liter of TSS. For most folks, that's not a problem. If your lagoon is producing effluent with 20 milligrams a liter TSS and you have to meet a 25 milligram target and you remove 25 milligrams of ammonia, you are still comfortably below your 25 target. So bottom line is most of these installations we're putting in, sludge removal is not a problem. The small amount of biomass you grow can go out with the effluent because it's a very small amount. The other question, cleaning the media, you don't need to. What happens is because it's a vigorously mixed system, that air grid keeps the basin vigorously mixed. The biofilm, when it gets to a sufficiently thick level, thickness, it'll slough off by itself. So there's no getting in there and cleaning it, or turning a backwash on or anything like that. It just sloughs off when it gets thick enough, and that's where those few milligrams a liter come from.
I have another question from Tim, and is the ammonia concentration directly related to the algae blooms in the lagoons?
No, those are two totally separate things. I can't claim to be a huge expert on algae. I think algae is generally a temperature-related thing. In my experience, algae blooms happen in sort of late summer or mid to late summer when the water is warm enough. The algae just starts propagating, and when you think of wastewater, it's full of nutrients. So that's what the algae needs to grow, is the nutrients that wastewater provides. So no, it's not really related to ammonia at all. There is a relationship there, though, which is around pH, and I briefly touched on it. When you have an algae bloom, it will significantly change your pH, and it generally makes it more alkaline, and that is when you have more of that ammonia in the unionized form. So that's when the toxicity can happen. So algae can be a problem when it comes to the toxicity of ammonia.
Another question, this is from Barnett. How was the result for LT50 or LD50 after the media?
What we've saw, so in Castleman, that was a requirement of their permit, and it passed the test. I haven't got the numbers off the top of my head, but when we've done this on the pilots as well, I wasn't involved in Castleman. I look after Western Canada. My colleagues in Eastern Canada look after that one. It's Ontario. For example, in Cold Lake, in the pilot we did there, we sent some samples for lethality testing from that pilot, and we had 0 fish kill. When you saw the effluent numbers there, the ammonia was very low, 1 or 2 milligrams a litre. As I said before, if you're below 5, you really shouldn't kill any fish in your test.
Thank you, Chris. Lots of people in the comments just really appreciated all the info you shared and provided.
Thank you.
Found it really useful. It was a really nice presentation. Thank you so much for coming to EOCP 2021 and sharing. I just want to put a call out to all the delegates watching. Is there any last questions for Chris? The one thing I did want to let everybody know is the links for the presentations we've had through the conference will be available on the EOCP website. So that's for all our delegates to know. And I just wanted to say thank you, everyone, for tuning in and attending. Please take time to do the survey and tell us how we did or what you think we did, and hope you had a great time. I think that's everything. There's going to be a final wrap-up goodbye from the main stage within the next 5 minutes. And thank you all. Share on EOCP 2021. Do your surveys, win your prizes. Stephanie, anything else? We'll see you in a few minutes and wait, but thanks everyone. Really appreciate you attending. Thanks
Thank you
so much, Chris. That was awesome.
Thank you.